Hello, in this tutorial we'll be comparing different characteristics to each other in Cognalysis MultiRate as well as comparing different models to each other in Cognalysis MultiRate. We'll be using as an example our same house price data that we used in the other tutorials. Looking at this upper right panel, for each characteristic that's included in our model we have a different value calculated here. We've got a significance, a factor count, fuzzy k, and effectiveness ratio. Let's look at this condition field. For significance, we're not talking about a statistical significance. Instead, what we're talking about here is a practical significance. Where are the factors very different from one, and where are those large or small factors in bins with a lot of exposure? So looking at condition, we've got some factors here that are farther from one. For one of these bins, though, we've got a factor that's pretty far from one, but there's not that many records in this particular bin. We're giving more credibility to these two. We've got quite a bit more exposure here, and so we're even though the factors may be smaller, this may be more important for us to understand this differential between 3 and 4. So what we're doing for this significance measure is looking at the absolute value between these factors and 1 and multiplying them times the exposure modified for all other characteristics, essentially telling us how much difference does this make for what we're actually trying to predict. Then summing up across all of the different bins together gives us our measure here for significance. We can then use that to compare the different characteristics to each other in terms of how important they are to this particular model. So I've got this sorted by significance. You can sort each one of these, but I have this sorted in descending order of significance. Zip code is topping the list because it has a lot of places where factors are far from 1 in places where there's a lot of exposure. Factor count is included here because we always want to be aware of how many factors we have in our model. We want to try to avoid model complexity. We don't want complexity for complexity's own sake. There's greater risk of overfitting and basically just complicating a model beyond what's necessary. So if we look at condition, we've got 6 different parameters being calculated here. But notice for this first bin, there is actually no data in that bin. We have a parameter for it, but it's not actually adding to the complexity of our model at all. And there's no risk at all of overfitting from it. And so the parameter count would actually include that, but this fuzzy k, which is a generalized parameter count, will not. We're actually making adjustments here to reflect the fact that credibility is coming into play and smoothing as well. So this first one, there's no credibility because there's no exposure. We really don't have a parameter. It's not being included. In this second bin, where the condition equals 1, we only have 21 records. Our observation adjusted for all other variables is telling us a factor of 0.733, but we're only using a factor of 0.914 because of credibility, which is a very important actuarial concept. We are actually saying that this particular bin only has credibility of 32%, and so we're only going 32% of the way from 1 to what we're coming up with adjusting for all of the variables. Together with that, then, we are only going to count this as being a generalized parameter count of 0.3. We're not going to count it as a full parameter count because our overfitting potential is less because we're not using as much of the data here. Also, smoothing comes into play. When you have smoothing across bins, you're also going to be using neighboring information, and therefore you're having less information that's tied just to some specific data for that bin. And so that impacts the fuzzy k calculation as well. And so we're summing those up across the different bins to get a generalized parameter count, but then we're also subtracting off in total from the fact that we're averaging these out to 1 and we're rebalancing them. So if you think about the case where maybe you only have 2 bins and there's 2 factors that are coming out, it's really the differential between those two. So essentially only 1 parameter in our model. So that's what this fuzzy k is getting at, is a generalized parameter count, and so we can use that to say which of our variables is adding to our model complexity. This one, fraction of basement, is actually just fitting a straight line. We used a linear relationship across the bins. That really is just one parameter. And so we can use that to see where we're getting additional complexity into our model. And then this final column is the ratio of significance to fuzzy k. So think of that as being how much predictive modeling bang are you getting for your parameter buck. And so we can compare across the different characteristics there. We might look at latitude and longitude and say, yeah, we're getting a certain amount of significance here, but we also have a fairly large number of parameters, a fairly significant amount of additional complexity being added to our model. Let's turn our attention now to comparing different models to each other. To do so, you go into the Tools menu, and within Tools, there's an option for Compare Analyses. And we are going to select the Price 1 and Price 2. Price 1 was the original model we built. Price 2 was developed from using the Auto Improve function. And we've got those two models shown here. We've got a number of things across the top here. Relative net lift, we talked about in one of the other tutorials, is a measure of how well the model does at ordering the test data. Root mean squared error, average absolute error, and once again fuzzy k. We want relative net lift to be high, we want root mean squared error to be low, we want average absolute error to be low, and we want fuzzy k to be low as well. So we're bolding whichever one has the best value for each one of those individual measurements. Notice that Price 2 here is being bolded as well, and that's because it has the highest ratio of relative net lift to average absolute error. We want this to be high, we want this to be low, and so we use the ratio of one to the other to try to accomplish both of those things. Root mean squared error is really just being included here in case you're interested in it, but because it can tend to be subject to outliers, we're not using that to actually indicate which one MultiRate is considering to be the best fit. Also notice there's a yellow shading here. The yellow shading is saying, well, it's possible that we could have another model that doesn't fit quite as well on the test data, but is close enough in terms of a statistical measurement they consider to be very similar to the best fit and has a lower fuzzy k. So the yellow one is the simplest model within tolerance of the best fit. In this case, though, the one that is the best fit also is the simplest within tolerance. Price 1 is simpler, but the difference between the two, if I double-click on both of these, is such that it's being rejected. So that simplicity that we're getting from being with the Price 1 model isn't worth it, and that's why this one is being identified as yellow. Also, when I double-clicked on those, notice that we have a lot more information that's showing up. We can see what the difference is between the two different models in terms of what was selected. Also sorting in descending order of significance where the factor is the most difference. So this is a helpful tool for comparing models when there's only two of them. It's a little less interesting, but you can compare more than that. We'll give some more examples here. So let's say for this particular model that we want to see what happens if we get rid of zip code. We want to see how important that field actually is to our model. And so we could right-click on this and say Trim Characteristics. So we'll trim that out, and we can restart our model. Notice though that our Auto Improve is still set to run. If I just want to create this one model, I don't want to then go in and have it create additional models after that, I'm just going to change that to none. So it just runs this model. The other thing that we're going to want to do here is call this a different name for this particular model. We'll call that Price 3 and have that start with price 2 as a starting point. All that does is we expect, since we just made a adjustment to price 2, we expect this model to be fairly similar to price 2, so it's a little faster if we select that as being the one that it uses for its first iteration and then adjusts from that point. Then we can press the Start Analysis button here to kick that off, but I've already done that. I've already created that model actually, so we're just going to compare that directly, and we'll see what that comparison shows. So between price 2 and price 3, the only difference is that price 2 includes zip code. We can compare how it does on a number of different statistics, training data or test data. The test data is summarized up here. And we can see that it was actually a worse relative net lift to price 2 when we got rid of zip code, considerably higher average absolute error when we got rid of it. The root mean squared error increased as well, but it did get simpler. The problem is between the two, it's found to be a very different model, not similar statistically to what we had for price 2. If it was, then maybe that simplicity would be okay. We'll do another example here. Let's open up price 2 again as a starting point, and let's say that we want to look at some of these other ones, because we have zip code, latitude, longitude, and combination of latitude, longitude, and we ran the auto improve process. It didn't suggest getting rid of any of these, but we might want to just look at it on our own. And so let's look at the one that has the lowest significance of any of those geographic fields. Let's take a look at longitude and getting rid of that. So same thing, I can trim characteristics here, get rid of that one. This time I'd maybe call it price 4 because maybe I want to keep price 3 in there, and again have that start with price 2, kick that off, and again I've done that one as well. So actually I'm just going to open that one up, show what that one looks like. And we can run our compare analysis here, and we'll include all 4 of those now. And what we see now is that even though this is a slightly worse relative net lift and a slightly worse average absolute error than price 2, if I compare the two, it's finding that when we run a Kolmogorov-Smirnov test, actually this is using bootstrapped test records, and I look at those same measurements, the same ratio, they're essentially the same model. There's a 98% chance that you would see the sort of differences that we are seeing just randomly from bootstrapping on the test data. And so it's saying, okay, in that case, the fact that we're able to make this model simpler and it's essentially as good, let's go with price 4. That's why this one is being highlighted in yellow. And then we might, maybe we decided to go farther. If we got rid of longitude, maybe we should also try to get rid of latitude. We've got this combination of latitude and longitude. If we get latitude out, we might be missing something that we're picking up because of the smoothing, and additional credibility we get. But let's test it. Let's get rid of that one too. And so we'll trim characteristics, and we'll call that price 5 and have that based on price 4. And we could kick that off. Again, I've already done that, so let's just compare it in the comparison tool. And in that case, it's saying, all right, we did make a simpler model by cutting out some additional parameters, but now the difference that we're getting between our best fit and this new model has dropped to a level where it's unlikely that this would be caused just from randomness. That actually we're getting additional predictive power, even though we have latitude crossed with longitude, and even though we have zip code, which has obviously a geographical component to it. Having latitude by itself in there as a variable, picking up credibility across different latitude longitude combinations, but within the same latitude, results in a beneficial model adjustment. So it's saying in this case we would still just go with price 4. So that's how you can compare different models to each other. You always want to be aiming towards the simplest model that you can, that does a good job of explaining what there is to explain. You don't want to add model complexity. You want to be aware of how well you're doing on the out-of-sample data, which is what we concentrate these compare analyses on, and you want to pay attention to which variables actually are driving your predictive power. Hope you found this useful, and happy modeling.